Thanks. So now next speaker is Vincent Vennin. Are you around, Vincent?
Yes, yes, I'm connected. Can you hear me okay?
Hi. Yeah, I can hear you fine. Maybe you can share the,
Yes. Yeah.
Perfect. Yeah. Oh, maybe you can make a full screen. Yeah.
So can you see my
I can see
around?
Yeah. Yes.
Okay, very good.
Okay, so you're starting a bit late, and you'll have 40 minutes, and then maybe 5 minutes per question. So I'll inform you maybe a few minutes before 40 minutes.
Okay.
Yeah. Thanks. So we are very happy to have Vincent Vennin, who's going to tell us about cosmic structures and quantum mechanical origins of cosmic structures. So, yeah, please take it over.
Well, thank you very much, and thank you for the invitation to present my work in this very nice conference. So indeed, I'm going to talk about the quantum origins of cosmic structures and whether we can prove that they come from some quantum mechanism. So I will just start by a brief introduction of cosmology, because you're all very well aware of the topic, and we've had already very nice presentations. But just to remind you that the way that we understand the formation of cosmic structures in the universe is from the gravitational collapse of primordial density fluctuations. And those density fluctuations are supposed to form from the gravitational amplification of quantum fluctuations in the very early universe. So this is usually described in the context of inflation, even though I will argue most of what I say will be even more general than inflation, but just to be explicit, I will consider inflation in practice. So during inflation, the Hubble parameter, which is this A dot over A, which A is the scale factor of the homogeneous and isotropic expanding universe, this Hubble parameter is almost a constant. And this Hubble parameter is in fact what gives you the typical length scale or the typical time scale which characterizes the expansion. Therefore, it characterizes the curvature of space-time. So now if you put a quantum field on top of this expanding background, and if you Fourier expand the quantum field in various Fourier modes, what you find is that the physics of each mode very much depends on whether the wavelength associated to that scale is smaller than the Hubble radius or larger than the Hubble radius. If it's smaller, it means that the physics is locally the same as in flat space-time, which is the same as saying that if you perform an experiment in your office or on your table, you don't have to worry about the fact that the surface of the Earth is curved. But if the wavelength is larger, then you start to feel the effect of the curvature, which amounts to saying that if you want to measure, I don't know, distances between Paris and some city in India, well, of course, you have to account for the fact that you're traveling around a curved surface. Now, what happens during inflation is that you have a transition between this regime on the left-hand side and this regime on the right-hand side. And when you reach this regime on the right-hand side, then you have a quantum field on top of a curved background, which typically results in particle production, quantum particle production. So this is a sketch of what happens during inflation. The Hubble radius is almost a constant. The wavelength grows as an effect of the expansion. Initially, it lies inside the Hubble radius, so it feels a locally flat space-time. So you can set up your initial conditions in the vacuum state of this effective Minkowski background. And then at some point, it crosses out the Hubble radius. It starts to feel the effect of the expansion, and you have quantum particle production, which occurs on super Hubble scales. And this gives rise to cosmic structures. Now, this is a mechanism which is very efficient at predicting a number of statistical properties for primordial density fluctuations. And those predictions are in excellent agreement with observations, and therefore we conclude that this mechanism is probably one of the most likely explanations for what we observe in cosmology. And everyone is very happy with it. But at the fundamental level, it is not a trivial mechanism, since it relies on using quantum mechanics on cosmological scales. And this raises a number of fundamental issues, such as, can we trust quantum mechanics at those scales? We know it works well in the lab, but we have never tested really quantum mechanics on distances of the cosmological distances and cosmological typical energies. Then there is another question which has to do with the fact that when we quantize fluctuations, we also have to quantize metric fluctuations, because general relativity is a diffeomorphism invariant theory. Therefore, the only gauge invariant quantities are combinations of fluctuations in the matter content and in the metric sector. So we have to quantize metric fluctuations, and this may not be trivial. And there are other issues related, for instance, to the quantum measurement problem, namely the question of why does a specific classical configuration emerges out of a quantum superposition. So in the lab, it's sometimes said that, well, if you believe in the Copenhagen interpretation, then an external observer acts on the wave function and make it collapse to one of the possible outcomes. But of course, this interpretation is a little bit hard to follow in cosmology because, well, obviously there is no one to perform an experiment on the wave function of the universe at early time. And if you really quantize all the field of the entire universe, then there is no external body or observer that you could refer to. So this also raises some, say, open questions about whether quantum mechanics can really be used in this context. Therefore, it will be interesting to test this strong assumption of the model. A side comment that I would like to make is that those questions apply for inflation, but in fact, they apply to most alternatives to inflation, which also rely on the amplification of quantum fluctuations to account for cosmic structure. So that would be true in, say, contracting cosmology, the periodic model, so on and so forth. So this is a rather strong statement, and was, as we often put it, an extraordinary statement requires some sort of extraordinary evidence. Of course, what people usually implicitly assume is that because the consequences that you can infer from this idea are very much consistent with observations, it gives some sort of indirect confirmation that cosmological structures have a quantum mechanical origin. But this is only an indirect confirmation, and what we would like to establish is whether there is some direct evidence. So this has given rise to a huge body of work since, well, since a few decades ago. And here is a list of a few, say, angles through which the topic has been addressed, and a list of relevant people. Of course, I'm forgetting a lot of very relevant names. I'm just listing a few people just to show that there have been a lot of work on this. But it has given rise to, yeah, I mean, a big amount of very interesting works. So the idea is that we know the quantum and the classical words are different, and one way by which they differ is by the nature of the mathematical properties of the correlations that they allow for. So one example is, you know, the Bell inequality, where in quantum mechanics, you can produce pairs of entangled spin particles. And if two observers, A and B, measure the spins of those two particles at different locations in different directions, and then if they compute the correlator between the result that they find, then this correlator should obey certain classical properties, which is known as the Bell inequality, and this sort of inequality can be violated in quantum mechanics. That's an example of correlations which acquire certain properties in quantum mechanics that you cannot reproduce with just a classical probabilistic theory. So the idea is that similarly to this, can we try to detect some quantum correlations in the primordial density field that would reveal that they have a quantum mechanical origins? So one way that we measure primordial fluctuations is through the temperature and isotropies of the cosmic microwave background. We have this measurement, this map, and if we look at the primordial field in different locations, we can compute the way that it is correlated in different at different places. So those correlation functions contain something about the quantum origin, their quantum origins. So there is a first question that you can ask, which is, before trying to see how we could detect those quantum correlations, maybe one thing we should ask is, according to inflation, is there something quantum that we should be trying to detect? And a generic tool to address this question has been developed now 20 years ago, but it has given rise to more recent developments. And it's called quantum discord. It's something which has been developed by people working in quantum information theory, and which is a tool to address the presence of quantum correlations between two subsystems A and B. So I will briefly explain how this is defined. Of course, I will skip most technical details, but just because it can be a little bit more involved, but just to give you a flavor of what quantum discord is. So the idea is that you have two systems A and B, two subsystems A and B, which can be in different configurations that I call AI and BJ for A and B. And you want to measure the amount of correlations between those two subsystems. So let's first do it at the classical level and then see how it can be done at the quantum level. So let's first imagine that this is just classical things, right? So at the level of, at the classical level, you can define the state of A in terms of certain probabilities associated to the configuration AI. You also have joint probabilities, P of AI Bj. So P of AI is just P of AI Bj, where you marginalize over J. And then you can define this von Neumann entropy, which is the sum of P of AI log of P of AI, which measures the information you have about the state of A. So this is a positive quantity, and it vanishes when only one of the AI is 1 and all the other ones are zeros. And so when the entropy vanishes, then it means that you know for sure what is the state of system A. So the system A is entirely determined in that case. And there is this relationship which you can show, so I'm not going to show it, but it's rather intuitive, which tells you that the information that you have about the joint system, A and B, is the same amount of information you have about the system B, plus, sorry, there is a typo here. It should be the information you have about A once you have measured B, right? So this is just a rephrasing of Bayes' theorem. And this relationship will play some role. So now let's try to build a quantum equivalent of this formalism. So in quantum mechanics, we do not describe states by probability distributions. We'd rather describe them by density matrices. In the same way that you can trace over a B here, the density matrix, which describes subsystem A, is just a full density matrix where you trace over the B sector. You can still define a von Neumann entropy, which this time is going to be minus the trace of rho log rho. It's again a positive quantity. It vanishes only if the system is in a pure state. So when you have a vanishing von Neumann entropy, then okay, it's a pure state, so you know for sure what is the quantum state of your system. But now this relationship that I wrote before doesn't hold anymore. To convince you that this is the case, let me consider a very simple example, which is the one of an entangled spin system. So I look at two spin particles and I consider the state which is a quantum superposition of both spins are up and both spins are down. Because it's a pure state, that guy, the von Neumann entropy of the full system vanishes. But now you can compute rho B, which is just the trace over A of the full density matrix. And then you find this, which is a pure statistical mixture. You see you have 1/2 probability that B is in the up configuration and 1/2 probability that B is in the down configuration. So if you compute the von Neumann entropy of that state, you just find log 2. And there you can see that this relationship must be broken because S of AB is 0. Then you found that S of B is 2. And this guy has to be positive, therefore this cannot be satisfied. And the fact that this relationship breaks down for quantum correlations hints that you can define a quantity which is called quantum discord, in which evaluate this relationship. So you define quantum discord as being S of A / B plus S of B minus S of AB. It should vanish in the case of classical correlations, but otherwise it does not. And so when you find a non-vanishing quantum discord, it tells you that you have some quantum correlations which are here in the system. Here you may notice this pi j operator. This is just a small technical subtlety, but in quantum mechanics, when you measure a certain system, you need to define the way that you measure it, right? Because operators do not commute. So if you measure the position of a particle or if you measure the momentum of a particle, it's not the same thing. And the state in which the system is driven is not going to be the same. So a priori, this object depends on the set of projector, pi j is a set of projector operators which describe the measurement process. And we minimize over all possible sets of projectors such that if we have a non-vanishing discord, it really means that whatever the way you measure your system, you will find indeed those quantum correlations. So the first step that I would like to follow is to use this tool and apply it to primordial fluctuations to see whether we have a non-vanishing discord or not. Because if we find a very small discord or a vanishing discord, then I think it terminates the talk, because it tells you, well, we won't be able to detect anything quantum. So we describe cosmological perturbations in this way. We introduce fluctuations in the metric component, fluctuations in the scalar field component. We build one of those gauge invariant combination, which here I take as being the curvature perturbation zeta. Then we extend the action and we derive the following Hamiltonian, where the field has been expanded on creation and annihilation operators, ck, dagger, and ck. And we find this expression. So we find, because it's a sum over k, this is that linear order and perturbation theory. Essentially, what we find is that the scalar field can be described in terms of a set of independent parametric oscillators. You have one oscillator per Fourier mode. The first term in the Hamiltonian is a free term. You see it does not create or destroy particles overall. You create a particle with momentum k, and then you immediately annihilate it. And then you have this new term, which is an interaction term between quantum fluctuations and the classical background, which either create a particle with k and create a particle with minus k, or destroy such a pair of particles. Because of statistical isotropy, if you create a particle with momentum k, you need to create a particle with momentum minus k, which is why those operators appear in this combination. And the coupling constant in front of that guy depends on the scale factor, and epsilon 1, which is the rate at which the Hubble parameter increases. So in a static universe, this guy is 0, but because the universe is expanding, this gives a non-vanishing contribution, which can be interpreted as a pump field or a time-dependent coupling constant, which leads to the production of particles. So if you use this Hamiltonian and plug it in the Schrödinger equation, what you find is that the solution of that Schrödinger equation is as follows. The wave function of your curvature perturbation is placed in a two-mode squeeze state, which is just the product of a two-mode squeeze state for each Fourier mode, where psi k is given by this expression. So you see that it's made of states which contain n particles in k and particles in minus k. This is, well, again, to preserve statistical isotropy. And in this sum, you have two parameters which appear, rk, which is called the squeezing amplitude, and phi, which is called the squeezing angle. So you see that you have entangled states. So entangled correlations between k and minus k, which is encouraging, because we know that entanglement usually gives rise to some quantum features. And those parameters r and phi, they depend on time as inflation proceeds. So this is, for instance, what happens for the squeezing amplitude r as a function of the scale factor. So this guy here corresponds to the time when the scale that I consider crosses out the Hubble radius. At early time, the squeezing amplitude is almost 0, which means that the only state which appears in this sum is the one when n equals 0. Therefore, it's the one with 0 particles. So it's the vacuum state. But then, as soon as the mode has crossed out the Hubble radius, r starts to increase, which means that you populate a state with higher and higher number of particles. So this is particle production. Note that those two-mode squeeze states, they are well known. They are used in quantum optics, for instance. But the amount of squeezing we can reach in the lab is, I think, at best now of order a few, or is maybe, I don't know, four-ish. But in cosmology, for the scale that we see in the cosmic microwave background, this R reaches values of order 50. And this is a logarithmic scale, right? Because it appears with this tangent function. So it's really you know, one of the, I think, the strongest Swiss state that one can produce in nature, presumably. Anyway, so because you know the wave function, you can compute everything, the von Neumann entropy and so on, and then you can compute quantum discord. So I skip, again, the technical details, but this is the expression that you get here on the left-hand side. And you see that quantum discord only depends on the squeezing amplitude. So because you know how squeezing amplitude evolves as a function of time, you can work out how discord evolves as a function of squeezing amplitude, therefore as a function of time. And what you see is that it grows in such a way that when R is of the order 50, discord is of the order 150, which is again a huge number because it's a logarithmic scale, and which tells you that, well, again, this two-mode squeeze state of the CMB is probably the most discordant state that one can produce in nature. So if I stop the talk here, then I guess, or at least if I want to draw some intermediate conclusion, that intermediate conclusion would be that the CMB should be placed in a very, very highly non-classical state because it has a huge quantum discord. And therefore, the next question is, well, can we try to violate some Bell's inequalities with the cosmic microwave background? That would be the experimental proof. So I'm just keeping an eye on time. So let's try to violate Bell inequalities. So this is just a reminder of Bell inequalities. I have two spin particles, A and B. I measure the spin in different directions. I correlate the result in some way. And then I have this inequality that should hold classically. Expectation value of B is less than 2. So here I can try to reproduce this sort of experiment. It requires to have a bipartite system, but here we have K and minus K. We know K and minus K are entangled. They are entangled because they are placed in a two-mode squeeze state. And therefore, it's it provides us with a playground which a priori allows us to build Bell operators. Of course, Bell operators are constructed from spin-like operators, and we don't have a spin particles. We have continuous variable, which is like the temperature fluctuation. This is a continuous quantity. So the first step is to build a spin operator out of a continuous spectrum. And there are several ways to do that. I will just, for illustration, show you one of those ways, which is which has been proposed by Larsson. So the idea is rather natural. You take your continuous spectrum, you split it into intervals of size L. L is a free parameter, which you can choose to be whatever you want. And then you measure your continuous variable Qk, and you see in which interval it falls. And then you just assign signs, +1, -1, +1, -1. And depending on the interval in which the measurement falls, then you return either +1 or either -1. So mathematically, it's defined like this. Each interval is of the kind NL, n+1L. You perform a measurement of Qk. It gives you n is like associated to this blue bar on the left of your red measurement. And you just return -1 to the power n. So this can be, written in that way. That's the expression of this SZ operator. SZ squared is 1, of course, so you can show mathematically. So it's a good candidate for a spin operator. And you can, in fact, introduce this S plus operator where you just shift the bra here by the amount L. This leads to Sx and Sy, which is just the sum, or the Hermitian and anti-Hermitian components of this S plus operator. And then you can show that those three guys, Sx, Sy, and Sz, they satisfy the SU2 commutation relations, so they obey the spin algebra. They have the same Lie algebra as spin operators. Therefore, if you use them, you will be able to construct a Bell operator. So what happens if you take this Bell operator and measure its expectation value on a two-mode squeeze state? So this is what we find. So on the left, so this is taken from this paper together with Jérôme Martin. So on the left panel, you have the expectation value of the Bell operator as a function of this free parameter L, and different curves correspond to different values of the squeezing amplitude or the squeezing angle. So you see that you have some configuration. For instance, let's take the brown line where R is 3 and phi is 0.04. So you see that along that line, you cannot find any value of the L parameter for which you have violation of Bell inequalities. So it means that if you work with such a two-mode squeeze state, you won't be able to violate Bell's inequalities. However, you have other configurations, like for instance, this light blue line, for which you do have violation, right? Violation is this dark line here, B equals 2. When B is larger than 2, you have violation. And in quantum mechanics, it can never be larger than 2 square root of 2, which is why there is this other line here. So then the question becomes, what are the values of R and phi for which I can find a parameter L which leads to violation? And the answer is given on the right-hand side panel, where for each, so this is a map in the parameter space R and phi, squeezing amplitude, squeezing angle. In each point of this map, the color stands for the maximum value of the Bell operator, where I have maximized over the L parameter, right? So I take the, I optimize L in such a way that I have a maximum value of B, and this is like the maximum. So the dark blue region is where there is no violation, never, there is no value of L for which you have a violation. But this colored region is such that there is a violation. And when it becomes dark red, then it means you have a very strong violation. You're very close to this 2 square root of 2 bound. So now the question is, of course, well, during inflation, what happens? Do I fall on the blue region? Do I fall on the red region? And it turns out that the answer is not so simple, because as inflation proceeds, R increases, as I've pointed out earlier, but also the angle decreases, phi decreases. And in fact, the rate at which it decreases typically, at least in a de Sitter kind of expansion, is that phi goes like exponential minus R during inflation, at least if you're close to de Sitter. But exponential minus R is also precisely the slope of that white line here, which is just an analytical approximation for the boundary between dark blue and red. So it means that, in fact, depending on the details of your inflationary potential, depending on the details of Searle corrections, you will either fall in the dark blue region or in the dark red region, right? But nevertheless, it's not difficult to see that for, say, potentials that have been now selected out by the data, such as plateau potentials, like the Starobinsky model, for instance, then you fall on the right side of this white dashed line, meaning that you can indeed, in principle, violate Bell's inequalities. So this is all very encouraging, and you might think, okay, let's do it. Let's perform this experiment. But in fact, there are two reasons why the answer is not yet complete. The first reason is that, well, in fact, we don't really measure correlations in Fourier space. In practice, we measure correlations in real space. Moreover, in the Bell inequalities assumptions, there is the notion of locality, right? So when you show that the inequality holds, one of the assumptions you have to put forward is that your theory is local. But the theory is local in real space. It doesn't mean that it is local in Fourier space. And in fact, it's not. In general, a theory which is local in real space is not going to be local in Fourier space. Therefore, if you find violations in Fourier space, well, it does not really tell you that, it could just be that you work with a theory which, although is local in real space, just happens to be non-local in Fourier space. So somehow, we need to redo this analysis in the case of spatial correlation. So instead of looking at correlations between K and minus K, we should be looking at correlations between one region in the CMB and the other region in the CMB. Of course, there is a good hope that this will still work because, we create entangled particles. Those entangled particles travel across the sky. So if we look at this, if we perform a measurement here and a measurement there should be still some amount of correlation, and there should be still some amount of entanglement. And therefore, we might hope that that the non-vanishing discord in Fourier space translates into some amount of non-vanishing discord in real space, and that the same goes on for Bell inequalities. So let me just describe quickly how the calculation can be done. So this comes from a recent couple of papers published a few months ago, and which is a very generic way which derives a very generic way to compute entanglement, entropy, quantum discord, Bell's inequalities, and so on, of quantum fields in real space. And the idea is rather simple. So imagine you have two locations in real space, x1 and x2. You have a field, which I call phi, and then I define the measured field at x1 as just being the field which is averaged over a sphere of radius r1. So why do I do that? It's because in practice, an experiment will have a finite spatial resolution, so you don't measure the field exactly at x1. In fact, you measure the field averaged in a certain region around x1. This is phi1, and the same goes for phi2. W is just some window function which selects, which selects the interior of this sphere here. Now you can show that, of course, you can do the same for the conjugated momenta, and up to some rescaling, then you can show that they satisfy canonical commutation relations, right? So commutator of phi I pi j is just I times h bar. I just take h bar equals 1 times delta ij. The only thing you need to do is to make sure that the support of the window functions do not intersect, right? So the two spheres should not intersect. Otherwise, of course, you have correlations between, say, phi1 and, the commutator between phi1 and pi2 will not be 0. But if you make sure that this does not happen, you don't have contaminations of, of degrees of freedom between the two spheres, then those canonical commutation relations hold. And then what it means, this is just a detail, that what it means is that you have built a bipartite system. It's like a two regular quantum particle system, which is in a Gaussian state if you assume that your field is in a Gaussian state, but that's the case for the two-mode squeeze state of inflation, that's a Gaussian state. And therefore, you can fully characterize the measurements at x1 and x2 with a bipartite system with a certain correlation, with a certain covariance matrix. And the covariance matrix is given by this expression at the bottom of the screen, right? So it's the integral in Fourier space of the some sort of Fourier transform of the window function times the power spectra of your field. Now, the crucial difference with the k minus k case is that the k minus k system was placed in a pure state, right? Remember that wave function was a direct product of wave functions for each Fourier subsector. Now, what you can show is that that guy does not describe a pure state anymore. And the reason is that, so meaning if you, for instance, if you compute rho squared, the square of the density matrix, you don't find that it equals rho. So this leads to this purity parameter, which is the trace of rho squared. This guy is 1 for a pure state, but it's smaller than 1 in general. And here it's smaller than 1. You can show from this expression. So why is that? And you see, it will play a crucial role in a few minutes. The reason is that the field is correlated in real space. So when you decide to perform a measurement of the field at two locations, x1 and x2, implicitly what you're doing is that you're tracing over the configuration of the field and the momentum in every other spatial location. And because there are correlations across the entire space, it means that you're tracing over regions, sectors of the theory to which you're entangled. And this, of course, leads to an effectively mixed state, as in decoherence. So it's decoherence not because the field is interacting with another field. It's decoherence because you decide to only measure parts of the spatial space. Well, nevertheless, you can carry on the calculation. The very convenient aspect of this formulation is that mutual information, quantum discord, and so on are well known for bipartite Gaussian systems. This has not been constructed in the context of quantum fields, but just if you take in quantum mechanics a two-particle system, you can design generic formulas for those objects, in particular in this paper by Adeso and Data 2010. So you can apply those formulas to this covariance matrix and then see what happens. So this is, for instance, a plot of quantum discord as a function of HR. So H is the, the Hubble scale. So this quantity on the horizontal axis is the ratio between the size of the region over which you're making your measurement and the Hubble radius. And different values, and alpha here is the ratio between the distance between the two patches and the size of the region. So when alpha is of order 1, it means that your two spheres are very close together. They almost touch each other. That would be for alpha equals 2. And when alpha is large, it means that the distance between the two spheres is very large compared to the radius of the spheres. So what you see is there are a few comments to make about this behavior, but one is that the typical values of quantum discord we reach are much, much smaller than what we were getting in Fourier space. You see, we reach values of order 10 to the minus 2, 10 to the minus 1, while in Fourier space, we were getting 150. And remember, it's a logarithmic scale, so it means that quantum discord has decreased by a huge amount. That's the first lesson we should learn from it. So there is much less, say, discordant configurations in real space than in Fourier space. And the second thing is that the way it evolves with HR and with this alpha parameter is telling you that the configuration that will maximize quantum discord is one when HR is of order 1, which means you have to measure regions of the Hubble radius, which of course is extremely, is impossible in the CMB, right? Because the Hubble radius at the end of inflation is much, much smaller than the spatial resolution of any realistic experiment. Most of the time you fall on this tail here, but still. And also that that it corresponds to values of alpha which are not too large, meaning that you need to consider close by location on the sky. Okay, so this is already a first indication of what's going on. Of course, you might say, yeah, quantum discord is not exactly 0, so there is still the hope that maybe we can see, that maybe we can see some Bell inequality violations, and well, in fact, the answer, unfortunately, is no. So this we have done with Lorenz, Esposito, Espinosa, Portales, and the paper is going to appear very quickly, I think in maybe 1 or 2 weeks. So we've looked at the Bell operator between those two measurements, x1 and x2. And here you see a map as a function of HR and alpha. And unfortunately, what you see is that it's never larger than 2. Right, so we don't find any violation in real space, unfortunately. There are some other parameters you can play with, such as the size of the observable universe, or there is also a parameter which tells you the way that the window function decreases, whether it's a sharp window function or a smooth window function. But even playing with those parameters, we find interesting behaviors, but we never find a violation, right? And we have really explored all possibilities there, so we can safely conclude that this does not work. Okay, so because my time is almost over, I just let me skip this. I just would like to make a final comment, which is the following. So even if we try to find a way to circumvent the previous statement, the problem is that one of the problems is that when you try to measure different spin operators, in some way you need to access information about the phase, and this requires to access information about the conjugated momentum, right? If you want to build something quantum, you have to have non-commuting operators. You have position and momentum. If you only have position, of course, you cannot find non-commuting combinations. You also need to have access to the momentum somehow. And in cosmology, the momentum happens to be described by a decaying mode, which becomes exponentially suppressed on certain Hubble scales, at least in the standard model of inflation. You can find maybe more involved models where the decaying mode is not so small at small scales, and maybe there is something you can do. But otherwise, in general, let me just skip that. In general, you have this problem of how could I reconstruct the decaying mode? So there is one question, which is could we detect quantum correlations by using position measurements only, which means without measuring the decaying mode? And you will see that the answer to that question will also maybe suggest a way to solve the previous problem. So it happens that there are in fact several kinds of Bell inequalities. The one that I've discussed is called spatial Bell inequalities, where you have two observers, 1 and 2, which measure spins in different directions, A and B, at the same time. So this kind of inequality is testing for realism and locality. And it does require a bipartite system, but it involves to measure the spin in different directions, right? So it cannot be done by measuring only position variables. This is what I've explained. Now, one could, and in fact, we've seen that in real space, those inequalities do not get violated, right? So we have two problems for them. One is that we cannot only rely on position measurements. The other one is that even if we could, we don't find any violation. Now, there are these other possibilities. One is called the temporal Bell inequality. It consists of measuring, there is only one observer, which measures the same system at different times in different directions. But this has two problems. One is that it doesn't test exactly the same assumptions as the regular Bell inequality. Namely, instead of locality, it is testing for non-invasiveness. And the other one is that it does not involve, again, measuring the spin in a single direction. You see A and B are different directions. So you would also have to access the conjugating momentum. Then there is this third possibility, which is called the Legge-Garg inequality, which consists in, again, measuring at different times the same system, but now you measure it in the same direction. You see A, it's always A here. So this is good because it solves the last problem we have, namely it relies on measuring only position variables, so only the curvature fluctuation for us. So that's good. In fact, we've studied this in this paper. And what we found is that, yes, there are configurations for the squeezing amplitudes at those three different times for which there is a violation of the Legge-Garg inequality in the two-mode squeeze state, right? So this is encouraging. And the fact, but there is, however, still this thing that it doesn't test for locality, it tests for non-invasiveness, which is a loophole that is more difficult to close. However, in this recent paper,
Vincent, sorry, can you wrap up in a couple of minutes? Then we have some time.
Yes, sure. Yeah. This is essentially my last slide.
Okay, thanks.
Yeah. So this last possibility was put forward in this recent paper with Kenta Ento, and it's called bipartite temporal Bell inequality, and consists in having, so you rely on a bipartite system and you measure your two spins at different times, but in the same direction. And then what you see that it is testing for realism and locality, so the same as the standard Bell inequality. But you can only measure spin in one direction if you want, which means that you can only rely on measuring the curvature fluctuation. No need to access the decaying mode. And that kind of inequality, we have shown that for two-mode squeeze state can also be violated. So this is nice. Of course, the only drawback is that now you can only measure zeta if you want, but you have to measure zeta at different times, which means that you cannot do it by only accessing the cosmic microwave background, because that would correspond to a single time, the time of the last scattering event. So you would need to cross-correlate those measurements with, say, other measurements at different redshifts, such as the large-scale structure, or, I mean, other cosmological probes. And this is, of course, probably experimentally challenging. So I'll just leave it here. Those are my conclusions. Just let me mention those two last points, which is something I've not talked about because I didn't have time, but just to mention that there are other things to investigate. One is about non-Gaussianity. So everything I've said so far assumes linear perturbation theory for cosmology. So the states in which my field is placed are Gaussian states. But if you could access non-Gaussian features, which arise from, interactions at cubic order in the action, this, in principle, also opens some room for quantum signals. And the other thing which I've not had time to mention is decoherence, namely the fact that because your curvature fluctuation field a priori couples to other fields that you do not measure, this leads to decoherent states, and decoherence is most of the time associated to a loss of certain quantum features. So that is also something that we need to take into account. Okay, so I think I will just stop here and thank everyone for their attention.
Okay, so let's thank Vincent for a fantastic talk. And maybe we have a couple of minutes. There is already a hand up. Shiram is first.
Hi, thank you, Vincent, for a wonderful talk. You had a plot of the quantum discord in real space as a function of h times r.
Yes.
In that, there was a, R is the scale over which you are averaging, correct? The window function.
Yes, exactly. Yes.
And what was the parameter alpha? I probably missed something.
Yeah, sure. Sorry. Yeah, here is the plot. So
It's
yeah, so alpha is the ratio between. So you see, so you have your two patches here. Each patch has a size r, and the distance between them is called d. And alpha is this d over r. So it tells you. So you see, when alpha is say 2, it means that the two patches are touching each other. And then when alpha is large, it means that the distance between the two patches is much larger than the size of the patches.
Right. And you are evaluating the quantum discord at the end of inflation. This evidently evolves with time.
Yes. So we did, we did different things. So in this plot, it's indeed it's at the end of inflation. We also evaluate it throughout the radiation era because it continues to evolve afterwards. But unfortunately, it does not increase afterwards. So it doesn't really change the conclusions.
I understand. Thank you, Vincent.
Raghavendra is next.
Yes, just a quick question in the same slide, or even after, you mentioned something about the decaying mode being very small, and hence the measure of discord or the inequality is hence very small. Can you comment about these deviations from slow roll models, which obviously can lead to enhanced decaying modes?
Yes.
Will there be?
Yeah, no, this is a very good point. So in fact, so in particular, I mean, and also, in fact, so what we learn is that from this analysis is that the place where you might encounter quantum effects is at scales which are of the order of the Hubble radius at the end of inflation. And by definition, those scales, they cross out the Hubble radius a few e-folds before the end of inflation. Now, a few e-folds before the end of inflation, we don't know whether slow roll inflation is valid. And in fact, it could be that there is a phase of so-called ultra slow roll, if you have a very, very flat potential. And we know that in such phases, like the role of the growing mode and the decaying mode is swapped.
Interchanged. Yes.
So the decaying mode starts to dominate over the growing mode in a sense. So you know that there are some, I mean, there is a range of scales in those models for which at the end of inflation, the growing and the decaying modes, they have similar amplitudes. So in that case, it means that, I mean, both these reasons, I think, tell us that that would be a very good place to look for quantum effects because, because they have a size which, and if the growing mode and the decaying mode have the same size, then okay, their commutator, there should be something which you can detect from their non-vanishing commutator and so on.
Okay.
Yeah, but of course, in practice, I mean, how would you access correlations at those small scales? I don't know. Maybe because sometimes in those ultra slow roll models, you also have production of primordial black holes because the fluctuations grow so large, and maybe the correlations between those primordial black holes, we retain something quantum, but okay, this is a bit speculative. But that's, I think, that's an interesting place to search for quantum signals.
Okay, thanks.
Okay, so if there are no more questions, then let's thank Vincent once again for a really nice talk.